Hey, everybody. Welcome to DCARI's 31st virtual fire investigative training session. Today we have Cameron Novak, who is going to talk to us today about gas explosions. Cam, go ahead and take it away.
All right, thanks, Bill. Yeah, so this is something that we've had a handful of experiences with at the FRL and me personally, and so it's something that thought it was worth getting some information out, putting a little bit of basic information out there, and some methodology type of stuff. And coincidentally, I've been exposed to some gas explosions in the past. The Minnesota IAAI chapter back when I was a little kid, so I didn't get a whole lot of interaction as far as helping and assisting with it at the time. But when our IAAI chapter had actually had the opportunity to blow up several houses over about 10 or 15 years and actually looked at gas migration within the structures and kind of the damage dynamics and what the resulting damage looked like from a gas explosion, both with propane and natural gas. So this is kind of built off of some of that, plus my own personal experience and research and everything else. So hopefully it's useful for everybody, and we'll go from there. So just kind of a preemptive caveat, and we're going to cover gas explosions, primarily fuel air, gas explosions with propane and natural gas. We won't be covering anything specifically to explosives, just because that's not my bread and butter. Although as far as some of the damage dynamics, a lot of the concepts are similar overall. So just kind of throwing that out there that this is not going to be about explosives. Just laying the groundwork for some background stuff, particularly with propane and natural gas, which are the two most common fuels that we're going to be dealing with in a typically residential or even commercial or an industrial explosion. Propane has a lower flammable limit of about 2% and an upper flammable limit of 9.6. So, approximately 2 to 9% or a 7% window of gas and air. The stoichiometric mixture which is basically that perfect mixture where all the gas and air are consumed in the reaction, is around 4%. The heating value of propane is about just shy of 2,500 BTUs per cubic foot of gas, which is just a little bit over or almost 2.5 times the heating capability of natural gas. Propane's heavier than air, and it's got a minimum of ignition energy of just about 1/4 of a millijoule. So, compare that to methane. Depending on and I should kind of preface these with these values kind of change ever so slightly depending on what reference you're looking at. But natural gas has a flammable mixture of between about 5 and 15%, or I think 4.5 to 14.5%. Again, depending on which reference you're using. The stoichiometric mixture is around 8 to 9.5% gas and air. Like I said, it's just over 1,000 BTUs per cubic foot of gas, and it's lighter than air. So it's going to rise in a structure. And the minimum ignition energy is just ever so slightly higher than that of propane. So just kind of some things to think about when we're discussing these and how they are going to react or behave in a compartment if you have some sort of leak. The minimum ignition energy, both of these figures, or the figure on the table, came out of the 2021 edition of 921. So you can see where the minimum ignition energies are. Again, natural gas is primarily methane. So that's where we typically pull its properties from. One thing that's worth noting, and I noted it on the previous slide, is the lowest minimum ignition energy values are going to occur at or near that stoichiometric mixture. And they kind of go up as you go to the lower or upper limits of that. And that's pretty much universal across the board. What's also interesting is that just that minimum ignition energy is actually a pretty small value. For comparison purposes, walking across the carpet and getting a static shock when you touch a doorknob can produce, 10 times as much energy as is necessary to ignite that gas air mixture. So it doesn't take a whole lot. And that's just something to be aware of, particularly if you have a suspected gas leak. You don't want to be messing around with turning light switches on or off, or trying to turn appliances off to minimize your ignition sources, because you might be creating one in the process. Another thing worth mentioning is how the ambient temperature might affect your flammable range. So as you can see here, as your temperature increases, your flammable range is actually going to broaden up, and your lower and upper limits are actually going to get lower and higher. So you get a larger mixture and a greater window for ignition to occur. Just something to be aware of. Furthermore, if your temperature drops, that flammable window actually starts to shrink. All right, so let's define what an explosion is. So 921 defines an explosion as the conversion of potential energy, whether that's chemical or mechanical, into kinetic energy. And that is going to result in either the production or the release of gases under pressure. And then those subsequent high pressure gases are going to do some work that ultimately have an effect on materials nearby. So we're moving, changing, or shattering, or somehow damaging nearby materials. There's two different types of explosions that we typically deal with. So mechanical explosions are the first one. And essentially, it's when a sealed container, ruptures or fails as a result of pressure buildup inside that container exceeding the limits of the container. So BLEVEs, or boiling liquid expanding vapor explosions, were a special case of that, where we've got a liquid in a container, and as we heat up that liquid, it starts to boil inside the container. And as we boil that liquid, we generate pressure inside the container. And at some point, that pressure buildup is getting to the point where the container just fails. Steam boilers are another example. Again, the thing is, they don't necessarily, these mechanical explosions aren't a result of some sort of combustion reaction or chemical reaction inside the container. It's just pressure buildup in the container that results in a failure of the container. Doesn't mean, in the case of like a BLEVE, we often see those with propane cylinders. So you can have a failure of a propane cylinder due to external fire impingement, that then the container BLEVEs and we get a big fireball. But that's still a mechanical explosion that just results in the combustion of the fuel inside the container once it's released. Versus what we're typically dealing with in a structural explosion is going to be a chemical explosion. So there's an exothermic reaction that creates a pressure buildup and heat, and those chemical reactions are creating changes and chemical changes in the fuel and air or the reactants. So again, typically fuel air explosions, whether that be gases or dusts, or we could have explosives with C4, TNT, all the other commercial explosives, or homemade explosives. But again, we won't be touching on those in particular in this class. We're just going to be addressing the chemical side of things with fuel air and gases. To make life even a little bit more complicated, we have different types of explosions, or the results of explosions. So we've got deflagrations versus detonations. So a deflagration is a propagation of the combustion zone at a velocity that is less than the speed of sound, or about 3,300 feet per second. And then a detonation is you've got a combustion zone that's moving faster than the speed of sound. So typically a lot of like explosives, your C4 and that stuff, they're typically more detonations. versus our propane and natural gas explosions typically result in deflagrations, although you can have a transition where that combustion zone transitions from a deflagration to a detonation due to some special circumstances. And we'll touch on that a little bit today. So the overall factors that are going to affect damage when an explosion occurs, really they kind of come down to what fuels are involved and what the characteristics of those fuels are. I think the biggest one is probably, or most important one is probably the fuel and air concentration. The second is the characteristics of that container or compartment or enclosure. So the size of it, the shape, what it's made of, and how strong it is all affect how much pressure is built up. The location and the magnitude of the ignition source also have a play, more so the location as opposed to how strong that ignition source is. Typically, we're not dealing with something where we have a very weak versus a very strong ignition source. It's hard to tell the difference sometimes after the fact, and we really don't know sometimes what the ignition source is. We just identify several potentials. The maximum pressure developed is obviously going to be a huge factor because the pressure is what's doing the damage. And then the rate that the pressure actually increases is going to affect how much damage is done as well. So we'll go through each of these independently as best we can. The fuel and air concentration is going to be a function of how much gas and air that, is it at the low end? Is it up on the high end, or is it rich? And how well is that gas mixed in the air are going to play a role in how violent that explosion will be. Testing and research has shown that the most damage tends to occur at or just above that stoichiometric mixture, which is roughly twice the lower explosive limit. And so, for natural gas, that's somewhere around 10% gas and air, and propane, it's somewhere around 4% gas and air. So just kind of reiterating, the NFPA 68, which is a guide on explosives or explosion venting and reducing or preventing damage, defines that stoichiometric mixture as a balanced mixture where ultimately we have no fuel or oxygen or oxidizer left after that combustion reaction. So all the reactants are consumed. It's that perfect mixture that we're shooting for. Leak rates and orientation. So if I have a more uniform mixture, I'm going to have if I have more mixing, I have a more uniform mixture of the gas and air, which allows it to combust a little bit better, as opposed to having defined layers where I might have one side of it that's a little more lean and another side that is a little richer, and some perfect mixture somewhere in the middle. It's not as stratified. So we get more uniform mixing when I have like a high velocity or a high pressure leak, or maybe I've got a natural gas leak at the floor. And so that, because it's lighter than air, it wants to rise in a compartment. And as it does so, it's actually going to entrain air. And that's going to help quickly create a more uniform mixture within that structure or that room. And then the same thing with a high elevation leak of a heavier than air gas. As that gas starts to fall, it might also entrain some air, although maybe to a lesser extent, but it will help provide some mixing that way. Where we have more of a layered approach is where we have the low velocity or low pressure leaks. And then if I've got, say, natural gas leaking at ceiling level, there's not much there to kind of force it to mix. And then the same thing with, say a propane leak or a heavier than air gas leaking at floor level. You also have depending on the orientation, if I've got let's say a natural gas leak with an orifice pointing down, it's going to shoot the gas down, but then the gas is going to want to rise. And same thing with propane. If I've got it pointed straight up, but then the gas is going to fall back down, that's going to help aid in the mixing. So here's this is a plot or a figure out of 921 that kind of describes or shows how the mixing can play a role. So on the left side, you've got a low momentum or a low velocity leak that develops a defined layer at the ceiling level. And here you can see where it's the various concentrations of gas and air, versus with a high velocity leak at the same level, you get more uniform or homogeneous mixing within that compartment. So that's just a function of what the momentum or the velocity of that leak is, and how does that aid in the mixing of that compartment. So here's some videos that a former employer of mine put together, the guys at Advanced Engineering Investigations, or AEI, and this goes through a couple of different minor or small explosions with propane, but looking at both the how much are we at the LEL, and then what is it kind of mixing, or how is the mixing done. So in this case, they've just dumped propane into this little compartment and allowed it to mix naturally through diffusion. So if you look at this, you'll see you've got ignition in the center. You've got a fireball that kind of goes out to the top first. And then because it's a heavier than air gas, you're going to have a higher fuel concentration at the bottom. So it may be too rich at the bottom to burn. And now it's burning from the top down, where the air and that fuel mix in that flammable range. So you see it just burns from the top down. So that's just a diffusion, natural diffusion, allowing those fuels to mix. Versus if we take that same 100% lower flammable limit propane mixture, and now we allow it to mix with a fan, or force it to mix with a fan, notice the difference in how it burns. Oops, missed the play button. So if you notice, it's a pretty significant change in how that gas burns. It pretty much, that fireball propagates from the center out in all directions, as opposed to propagating up where the fuel is mixed properly in that flammable range. And all that fuel is burned and consumed in a relatively short period of time compared to the same mixture in the other. Now, in this case, we've got 2 times, or roughly, that perfect stoichiometric mixture with propane, and this time it's mixed with a fan. So notice how much more, what the differences are between this and the last explosion. So quite a dramatic difference. Again, we're twice the concentration, around 4%, but it's mixed with the fan. But this is where we're at that roughly stoichiometric, or slightly higher than that gets that perfect most damage or most pressure rise from that explosion. And then here's propane at or near the upper flammable limit. So I think that one was probably mixed with the fan as well. But you'll notice just how much more fire there was or flame after the fact, just because how much propane or fuel there was to combust. And it obviously the flames had to extend out of that compartment in order to get all of that fuel mixed in the appropriate mixture in order for it to combust. Right. So this is kind of a lead into how the structure or the enclosure affects our explosion. And if you watch this video and look at how the fire or the flame front or the combustion zone, what it looks like as it starts from the ignition source. So it's a relatively perfect sphere until it starts to hit obstacles, and it goes from kind of a nice laminar flame to it becomes more turbulent. There's a lot more wrinkles, and then it hits the enclosure, and that overpressure actually causes that piece of wood to come off the window. And then when you see that flame jet hit that piece of wood, it actually deflects off of that wood and out and around from there. So when you have a mixture that ignites, naturally that fireball wants to radiate in all directions and create just basically a sphere. But as soon as that sphere starts to hit obstacles, you start to develop turbulence. The obstacles can absorb some of the pressure, and they can absorb some of the heat. And so that can actually affect how much pressure is generated in that explosion. So research has shown that highest pressures are typically developed in a spherical enclosure with the ignition at the center, because that allows that combustion zone the greatest amount of room to start to build up that pressure before it starts to hit the enclosure wall. So a square, or I guess a cubicle room, is going to be most similar to a spherical enclosure, versus if I've got a long hallway, it's going to take a lot more time, and it's going to have a lot more surface area down that long hallway for that combustion zone to basically be cooled, and essentially the walls to act like a shock absorber and absorb some of that kinetic energy. The other thing too is a weak enclosure or structure is going to fail before maximum pressures can be reached. And so you're not going to reach your peak pressures if the structure fails and doesn't provide any containment for it. And then, we typically don't see much, if any, pressure buildup if I've just got a vapor cloud explosion or ignition outside in the atmosphere. There's nothing to contain it, because we need that containment in order to generate pressure. And then, if I've got the same mixture, fuel air mixture, in a small 55-gallon drum versus a 10 by 10 by 10 room, I'm going to create or have a faster rate of pressure rise in that small enclosure as opposed to in the larger enclosure, just because given the volume of the existing compartment. So I kind of already addressed this on the previously, but if I put my ignition source in the middle of a room as opposed to in a wall, against a wall, or in a corner, I allow that combustion zone to radiate outwards and generate the most pressure before it starts to get absorbed by the walls of that enclosure. And this is what this chart shows here. This is from the Kennedy on Explosions textbook. And so you can see, if I've got a spark, my highest pressures are generated with the spark in the middle of the enclosure, and I generate the highest, there's the highest pressure, and then the maximum pressure rise or rate of pressure rise here, almost 2 or 3 times higher than everything else. And so if I put the ignition source at the bottom, I still have the ability for that combustion or reaction zone to move from the bottom of the compartment up. Same thing with the side, shouldn't be all that much different. With the top, you see the least amount of pressure rise, and I suppose that's because you're fighting gravity, you're pushing everything down. But fairly significant differences in the pressures based off of where that ignition source is located. So another thing that's going to cause pressure rise and cause more damage is obstructions. So when a flame front or a combustion zone starts to hit obstacles, you're going to cause turbulence. The flame itself, or the combustion zone, is actually going to work around that, and it's going to cause turbulence and eddies. And now you get increased flame lengths, and every fuel has more or less a set burning velocity. So if I start to create a larger reaction zone, I'm now combusting more fuel. And so now my flame speed actually kind of increases, or my reactions increase. I get more fuel involved at the time, or at any given time. And now that everything kind of works faster, combusts faster. And so this is kind of a feedback loop that you get here. So if I've got combustion in the process, or combustion in the gas cloud, that expands due to the heat generated, that combustion zone is going to interact with obstacles. We generate turbulence. That turbulence creates more combustion, and then we get this nice feedback loop. There's increased pressure, which causes the expansion, and so on and so forth, to the point that things get a little crazy, let's just say. So here's an example. This is out of 921. And so showing how different types of obstacle arrangements can affect the pressure rise in a compartment. So you can see here's A, B, and C. Our highest pressure rise happens with this B arrangement. And then obviously significant based off of how much of that enclosure is actually blocked. So the blockage ratio is essentially a third of the volume is blocked versus half of the volume, or 50%. And you can see all of these except for this one, the C arrangement, result in a pressure rise at a higher blockage ratio. So kind of an interesting example. And you say, okay, great, you show me a graph. What does that show or equate to in real life? So Gexcon is a company that works internationally, and they're renowned for their explosion expertise, or expertise in explosion investigations. And so they've done some tests. And in this case, we basically got like a plastic sheeting over, kind of like a greenhouse, basically. And we've got a gas mixture in here that is in the flammable range, and it's basically wide open from end to end. So you'll see the difference here. There's no explosion or no obstructions in this enclosure. We'll play that again just because it's kind of short and relatively fast, but not ungodly fast, not super quick or anything reaction. But if we now fill this tunnel with obstructions, notice the difference in how fast that reaction takes place. So that's basically all that is a bunch of little trees down the center of that tunnel. So we'll play that again. So almost, this is just my rough, but that's, I would say, probably at least twice as fast as that prior reaction or explosion. So it's probably worth talking about the types of damage that we can run across in a scene. So low order explosions or low order damage is something you'll hear, low or high order damage. And what we're really talking about is low order damage is kind of the pushing, the moving of big walls, bowing of walls, window frames or windows just pushed out of their frames. Versus high order damage is basically you're turning a structure into toothpicks. And one of the key factors that determines the difference is how quickly does the pressure rise within that structure. And ultimately it comes down to how fast, if the pressure rises faster than the building or the enclosure can vent it, you're going to result in a lot more damage or a lot more high order damage. So, say I've got a relatively small explosion. If I've got a window that vents, or say the window pops out of its frame, I'm going to vent that damage and I'm going to have very little damage elsewhere in the structure. And maybe that's the only evidence of the explosion that I have is that vented window. Versus if I've got a very quick pressure rise, maybe even the window can't vent that quickly. And so the whole structure just shatters. So speaking of pressures, there's a couple of different references. On the left is from the Kennedy on Explosions book. On the right is a chart from NFPA 921, just looking at different types of pressures that are required to get various building components or cause damage to things. So, it takes roughly about 88 psi to cause a crater. We're going to have, let's see here, roughly around like say 1% or 1 psi, anywhere from a third of a psi to 1 psi, windows are going to be broken or dislodged. So we've kind of got the range of pressures here that we could be dealing with or see. And this gives us an idea of how we can estimate the amount of overpressure that the explosion caused. The other thing worth considering is when you have an explosion, you typically have a positive and a negative pressure wave or phase of the explosion. So most of our damage results from that positive pressure wave. So it's that combustion reaction and the pressure front moving away from the origin or the ignition location of the explosion. It's the most damage, or it's the most powerful part of that explosion. But as that pressure front moves away and that reaction front moves away from its origin or the epicenter, you kind of leave a little bit of a vacuum. There's a low pressure area behind it. So the negative pressure wave is when all of that air, after the positive pressure wave has gone away from the origin, we've left that low pressure area. So now all the air, ambient air, comes back in to fill that void and equalize everything. And so that air coming back in can actually move debris or objects back towards the ignition source or the origin of that explosion. And it is significantly weaker, but it's actually proportional to the positive pressure wave. So the stronger that positive pressure wave, the stronger that negative pressure wave is going to be. So here's just an example of what we would consider low order damage. And you might say, Cameron, that's still a pretty big explosion. Yeah, it is. But if you look, a lot of the walls, the walls didn't shatter. They just kind of kicked out at the top or the bottom and peeled away from the structure. Entire doors and windows were basically thrown out of their frames. That is consistent with low order damage like this. As you can see, the walls are still, yes, they've kicked out here. This wall kind of flopped out, but it's still almost completely intact, that you could almost put the wall back up and put the structure back together. Compare or contrast that with high order damage. And I think you'll see the difference. These are pretty dramatic differences. Don't mind the cheering in the background. So, I think it's pretty evident the difference in the damage here. You can't really recognize many large portions. I mean, this is probably the largest section. There's a bit of a wall here, maybe a bit of a wall here, but otherwise everything's just shattered. And that is the classic difference between low and high order damage. Okay. So low order damage we're typically see with mixtures near either the lower or the upper flammable limits. Where we tend to get high order damage is with mixtures near or just above the stoichiometric mixture. We also tend to get a lot of post-explosion fire with mixtures close to or above the upper flammable limit. So if you think about it, if I've got where my ignition source has to be is somewhere within that flammable range, but there are plenty of times where I might have an excess amount of gas in areas where either there weren't ignition sources or the gas was able to collect there by the time a flammable mixture reached an ignition source. But the explosion itself now brings that gas either into its flammable range, or I've basically opened everything up and now I have this excess gas where I already had a flame front, and now I basically just have these pockets of burning gas in trapped spaces. And it's common post-explosion. We've seen with the research that our state chapter has done, you could have pockets of gas in, if it's propane, it could be in like a sewer drain a floor drain in the basement. We've seen gases, both propane and natural gas, basically sit in cabinets or in closets or behind closed doors. And it just doesn't vent that quickly once the building blows up, if that compartment still or enclosure still stays intact. So we can now bring a rich pocket of gas into its flammable range, and then we can have either secondary explosions or just spot fires. So relevant codes that are going to be pertinent to us are going to be NFPA 54, which is the National Fuel Gas Code, and NFPA 58, which is the Liquefied Petroleum Gas Code. So those are things that might be pertinent in our analysis and our subsequent investigation as far as testing and proper procedures and everything like that. So here's just kind of a rough, overall view of how natural gas is getting to our homes. So we're going to have wells that are going to produce that gas. Basically, it's, we're getting that from our fossil fuels. We're separating it out. We can have underground storage for natural gas. We can have liquefied natural gas, propane plants. And then as it gets closer, we're going from transmission to the distribution level. Once it's gone to through these city gate stations, and then it gets distributed from there. So, and then as we get closer to our homes, we're going to have a main from the street that'll go into through a valve and a regulator and a gas meter. And typically, you're going to have that transition point from the ownership from the utility is going to be at the outlet of the gas meter. And that's where it transitions from utility owned to customer owned equipment. From a propane system, most often that's going to be trucked to your location, pumped into a tank, and then you will have one or two regulators that then allow it to get down to the pressures that you would need inside your house. So typically on a two-stage system, like at my house, I've got a first stage regulator at the tank, and then I've got a second stage regulator on the exterior of my house. You can also have a dual stage system where it's just one regulator that drops it down to the correct operating pressure. Different types of cylinders. So you can have, all of our cylinders are going to be basically built to either Department of Transportation or ASME specifications. And typically what we're dealing with at a residential setting, something like this, like a 500 gallon or 1,000 gallon tank. I happen to have two. I've got a 500 gallon tank for my house, and then I've got a tank, I think it's around 100 gallon like this for an outbuilding at my house. And then we can have both above ground or below ground tanks. So here's an example of below ground tanks that you now have access to everything above ground that obviously you would need to in order to fill it. And they do have overfill protection devices on the tanks inside and all the fun stuff associated with that. We've got pressure relief valves, filler valves, all that kind of fun stuff. So pressure regulators are kind of neat. And while the designs, the overall design is relatively constant, they're going to look relatively similar, but they're all going to have the same function. Really what it does is the regulator controls the pressure and the flow of gas based off of the needed pressures. There's a rubberized diaphragm in here. And on one side of that diagram, you've got a spring that you can adjust to get the desired pressure. And on the other side, you've got gas pressure pushing on that. And the two, basically the gas pressure and the spring pressure, are fighting each other to maintain that pressure. So the way these are set up, the red line is the pressure coming in. The blue side is the pressure going into the structure. So the way I've kind of looked at this is if I've got all my appliances in the structure are off, there's no gas flow. So I've got basically this static, I don't want to call it high pressure, but I've got a pressure here at lockup, which is the term for when I've got no gas flow. At lockup, I've got a pressure here that pushes on this diaphragm. And when it says, I don't need any gas, it's going to push on this diaphragm and say, stop right there. No more gas needs to come through. But if I turn an appliance on, I've now created a low pressure on this side, which now the low pressure allows the spring to fight and push against the gas pressure here. And what that does is it actuates this lever that now pushes the stop or the valve seat or opens it up and allows gas to move through downstream. And so that fighting between this spring here and the gas pressure here is what regulates our pressures going into our structure. And you can adjust that via this little set screw here. You can adjust how tight or how loose that spring is. There's also a secondary spring right here, and that's the pressure relief. So that holds the valve seat here. So if there's an overpressure event, that can allow the gas to actually burp out here and then escape through this atmospheric vent. And this is important because this vent allows the diaphragm on this side to move back and forth with the spring. If it were closed off, you'd now be fighting kind of the pressure of that sealed container as well as the spring, and so it won't work. And you need that to be open and not occluded, which is can result in some issues, typically high pressure gas downstream. We'll get into that in a bit. So there is pressure relief, as I mentioned, that allows, come on, now my mouse is getting away from me, that allows that relief vent to operate and allow gas to vent from that the vent. So we've got, if that vent is, say you've got your regulator inside a structure, you have to actually vent that to the exterior so you don't get basically a leak of gas inside, because that would be bad. So you have to sometimes pipe it for sure outside, but maybe it's got to be vented or piped to a specific location. So the failure modes, if the diaphragm fails, you basically have nothing to allow that spring and the gas pressure to work against each other. But that typically just allows the high pressure gas to flow out the vent to the atmosphere. and you may have some, you're going to have high pressure gas going into the downstream piping as well. So it'll be kind of a mixture of the two. If you block the vent, the diaphragm can't move freely anymore. So now the regulator isn't actually regulating. So now you are, it's not going to be operating properly. And so you can have high or low pressures downstream depending on how it's actually functioning or not functioning. If you get some sort of piece of debris in that valve seat, or maybe the seat is getting worn out, or just through age or wear and tear, now you can get gas that seeps past, even though maybe the regulator shut off. So now we're getting gas to continue into the high pressure piping. Usually that's going to, that may vent to the atmosphere through that pressure release valve in the vent. But you know, most of our appliances might be able to withstand that temporarily, but it will eventually burp out, and could lead to some issues downstream. So the two types of testing we can do on a regulator, we can basically flow pressure or flow gas on the outside and actually verify that we're getting the proper pressures downstream. We can also do lockup testing to ensure that it's actually working and not leaking. So we'll turn all the downstream appliances off, turn off all the pilot lights, so there's zero demand on the downstream side of the regulator. And we'll basically just do a pressure test, and do we see a pressure drop from the upstream side of that regulator. Typical gas meters, you've got the diaphragm meter here in the lower left. That's typically what we're used to seeing. As you get into the larger structures, you're going to see these rotary or inferential meters as well. And I'm gonna give a shout out to Jeremy Nagel, because at the FRL he put these slides in the upcoming video together, so kind of showing the operation of these diaphragm meters. But just kind of one preemptive thing, they are set or temperature compensated, so they've got they're all set for a particular temperature, and then they do automatically account for differences as the temperature, ambient temperature, fluctuates. So Jeremy took this meter apart and actually put clear covers on it, so you can actually see what's happening. And basically you've got two bellows. One, this is the front one, and one on the back. And those are connected to a set of sliding valves up top. And basically that's how you get your measurement here on the readout. So I'll play the video. It's kind of noisy because it's got air running through it, but so if you look closely, you'll see that basically this outlet side here is connected to this pipe. There's a little bit of a pipe underneath here. So your gas comes in on this side, and it goes in through these sliding valves. Work goes through the bellows, through a series of vents and channels, and then comes up this side. And that rotating here up top is what's getting your meter to spin and actually calculate or record how much gas is being used in that structure. Okay. The one thing that can be an issue is if you've got if you're in an area prone to a lot of snow and ice, like I am up north, you have to actually protect your gas components from damage. So this was I just happened to be out for dinner with the family, and the nerd in me saw this and said, I need to take a picture. But this is on a restaurant where the slope of the roof allowed snow and ice to fall off on this side. And if this little overhang weren't present, you could have snow and ice fall onto this meter and regulator. And if it were heavy enough and fell hard enough, you could actually break the piping, or maybe you don't break it out here, but you cause enough of a movement that you break the piping inside, leading to a gas leak. So that's just something worth considering. You also have to worry about in cold climates with a lot of snow, if the snow builds up and blocks your vents on your regulators, now that regulator is not able to function properly. It can't breathe like it should, and that could lead to some issues downstream. So gas meters, because they're outside the structure, they're not regulating anything. They're just measuring the amount of flow through the meter. So it's not, inherently an issue that's going to automatically lead to an explosion, unless that gas, leaks from a seal and somehow migrates into the structure that way. But they're inherently not going to cause a high or low pressure event unless you start to have some like obstructions in the piping or something like that. But really, your biggest concern is going to be some sort of bill issue. So this is something that's becoming more frequent or more common, is smart meters. And we've been using them a lot on the electrical side of things, but they are actually out there on gas meters and even water meters or other types of meters. And so you can typically, you may have to download the data from the meter module itself. It may get transmitted to the utility company, or maybe it's just they drive by in a truck and it pings off of a receiver in the truck. But the benefit to that data is something like this. And I'll preface this with, this is not the best graph, and it's a little cattywampus in that at the time of the explosion, this was the gas reading. This is like a month or two before the fire. So it's the x-axis is actually reversed. But you can see from a historical standpoint, you had some gas consumption, not much. And then the day of the fire, you had essentially 10 or 20 times the amount of usage prior to the explosion occurring. I think this is probably the consumption leading up to the explosion, and then the explosion occurred and you had broken pipes and a really high flow that way. So using something like this can be beneficial in that you can actually get a timeline of when the explosion or when the gas actually started leaking. I was actually talking to an engineer last week who said the same thing. They had an explosion where the occupant intentionally broke the line. And so they had, typical gas usage, something like this, maybe 10, 15 cubic feet per hour. That occupant messed with the meter or a gas line, it jumped up to say 100 cubic feet per hour, and it sat there, and then the house didn't blow up. So then that occupant went and messed with the gas line again, and it jumped up to 200. And then it sat like that for an hour and still didn't blow up the house. So they went and messed with it again, and it jumped up again, and eventually it did blow up. But you can see how they went back repeatedly and started monkeying with that gas line. From a testing standpoint, you can test, there's a couple different tests you can do to measure what kind of gas is being flown through your system. Utility companies have to prove a meter to make sure it's accurate before it gets placed into service. The easiest would be if the meter's not damaged, you can do a clock test of the meter to check for leaks or check what the leak rate is. So the different tests we can do, we've got a clock test, pressure drop, a soap bubble, gas detector surveys, bar hole tests, and odorant tests. So clock test is basically you turn everything off. All the appliances are off, all the pilot lights. You turn on the gas, you take an initial reading at that start of that time, and you turn a clock on for, say, 10 minutes. And then at the end of that 10 minutes, you look at what that final reader meeting is, and the difference is going to be however many cubic feet over that 10-minute time, and that's your flow rate in that period. Pressure drops just like it sounds. I turn everything off. I apply pressure to the system, and I monitor that for a few minutes, and then I see, is there a leak or is there not a leak? This picture on the right was actually at my own house. I just had new regulators I put on this summer. My second stage regulator was actually leaking. So the gas technician had this little gauge, kicked it up to 6 psi. We had turned everything off, let it sit, and you could see here it started to leak in that just 5-minute span that we weren't holding pressure. So we had an issue with my second stage regulator. Soap bubble tests, just like it sounds. I'm putting some sort of solution that generates bubbles when there's some sort of leak and air flows through it. If I find bubbles, that means I've got a leak. If I don't find bubbles, that's a good thing. Similar to a gas, the bubble test, we can, instead of putting bubbles on, or a solution on, we can basically use a combustible gas indicator to basically sniff out where a leak might be. So we're going to follow the piping. We're going to check at all the connections, stuff like that. Bar hole test is typically what the utility company is going to do. So they will map out and they'll punch a series of holes either in the ground or in the pavement, and then they will stick a tube in that hole, and they'll basically create a map as they go from, say, the meter out towards their main line in the street, and they'll show that there either is or is not any sort of gas available in the soil. You can also test for the odorants in the gases. You can use stain tubes. You can use special equipment like this odorator, or there's actually a way you can just sniff it manually. But that's probably this is probably, I would say, more so geared towards if you have a leak and people died, maybe we're trying to figure out, was there or was there not odorant available in the gas, and therefore why did these folks not smell it, or maybe they did smell it prior to the explosion. Just something to keep in mind, that the volume is going to be dependent on the pressure and the temperature. And so gas meters are going to can account or compensate for temperature or pressure measurements. I know a lot of times too, if you're using, say, an air compressor to pressurize your system, if that air compressor is hot, or the air you're putting into the system is hot, and then you do a pressure test, over time that air you've injected in the system is going to cool off, and subsequently you'll have a drop in pressure. If that temperature decreases, or pressure is proportional to that temperature, everything else being the same, so that pressure will decrease along with the temperature. So something to be aware of, that just because you've got a drop in pressure, you have to be aware of the fact that the gas might, or the air might change temperatures. Typically you can use both the fuel gas, as long as you can do it safely, or you might use something like compressed nitrogen, or just an air compressor or something like that. If you're using something other than the fuel gas, you have to account for the different gas properties when it comes to your leak rates. Typically, a pressure test has to be no less than 10 minutes. With a minimum of 3 psi, or up to 1.5 times the rated working pressure of that system. When we pressure tested my system in my house, it was 10 minutes at 6 psi. So we were twice that minimum. Odorants, both natural gas and propane are naturally odorless. So they have to, per code, add something to make it possible for the average person to detect it at 1/5 or 20% of the lower flammable limit by the majority of the population. The most common odorant that we typically hear of is ethyl mercaptan, but there's a few others that are also used based off of the application. And there's factors that actually affect a person's ability to detect or smell deodorant. So, the older you get, the worse your nose gets. If you've got a cold or allergies and it's allergy season, those are factors or complicating factors. If you've got other strong odors in the area, that can make it hard for you to smell it. Some people just naturally can't smell that particular odorant. There's actually been research that shows that when you're sleeping, your nose essentially shuts off. So if you have a leak that starts in the middle of the night when you're passed out, you might not note it. And then when you wake up in the morning, your nose has already essentially adjusted to it. And so you don't pick it up in the morning unless you go outside, get some fresh air, and then come back in. And then another issue is odorant fade or scrubbing. So new steel piping or tanks or cylinders can actually absorb the odorant until the metal gets saturated, and then it no longer absorbs that. And then soil can either absorb or oxidize the odorant. And if you've got an underground leak that migrates into the house, that soil can either pull the odorant out of the gas, or it can cause it to oxidize and basically degrade in its ability to basically be recognized. What's also interesting with underground leaks is gas can actually migrate quite a ways underground. So let's say I have a leak outside of my structure, but underground, that started in the summer. And that might not be a problem until winter comes and now the ground freezes and I've got snow and ice on top of it. Now that gas can't migrate upwards through the soil into the atmosphere, now it migrates laterally. And typically, in order to bury a pipeline or a gas line or something, you've had to dig a trench. And when you fill that back in, that soil is not going to be as compacted as the original soil. And so now I've got a pathway for that gas to migrate, and it just so happens to be towards my house along the pipeline or the gas line. And then you complicate that with the ability of the soil to either oxidize or remove that odorant. And now I might have a gas leak that I have no way of knowing about. So some signs of underground gas leaks: dead vegetation obviously is a indicator, because it actually removes the moisture from the soil, which can kill the vegetation. Obviously, if you hear a hissing noise, that would be an indicator. Smelling something would be an indicator. If you've got standing water and you've got some sort of bubbling up through the water, and then abnormally dry or hard soil, like I said, it helps remove moisture from the soil. So all those can be indicators of an underground gas leak. All right, so from a safety standpoint, don't smoke around a potential gas explosion scene. Don't manipulate switches or equipment. Don't turn anything on and off. Don't operate flashlights, radios, power tools, stuff like that. If you have to, turn your flashlights on outside and then walk in. That way you're not flipping a switch and causing a spark or anything like that that's going to ignite that gas. From a investigation standpoint, typically we want to start with interviews. So, talking to any either witnesses or occupants. What happened? Was anybody home? What were they doing? The sooner you can interview folks, the better, because not everybody survives long term, unfortunately. Typically, we're worried about, was there any recent work? That's probably the number one thing that causes explosions, is somebody working on the system right up prior to the explosion. Somebody trying to light an appliance where they turned valves on or off recently. Had they recently connected or disconnected the service? What appliances were operating at the time? Were there any problems with those appliances? Did you smell something that you didn't realize was the odorant? Specific to propane, when was the tank last filled? Was anybody home? At what point, or what was the level of the tank that they brought it up to? Was the tank empty prior to being filled? Usually when your tank's empty and it's leaked all the way out, the technician will actually have to do a leak test, and we'll have to check the pilot lights, and oftentimes we'll light the pilots for the homeowner. What was the weather like? What was the weather like at the time the tank was filled? And this is maybe, it can be an issue with large tanks, like residential size tanks, but where we see it a lot is with like 20-pound cylinders or maybe 100-pound cylinders on the back of food trucks. If you overfill a tank because you don't know how, and then let's say you fill it on a cool day, but then you put that same tank out in the hot sun, the pressure in that tank is going to increase. And if you don't leave enough vapor space for that gas and vapor to expand inside the tank, you can actually overpressurize that tank and cause it to fail just from the solar gain heating the product inside. So they have to, there's limitations on how full you can fill a propane cylinder. Again, if the cylinders were involved, where were they? When were they last filled? How were they filled? Where? They do volumetric or weight-based fills, and essentially it's only supposed to get filled up to 80% to leave that wiggle room for the gas to expand as it vaporizes due to temperature fluctuations. All right, from a scene examination standpoint, you say, "God, Cameron, we're talking about a lot of other stuff. Let's get to the meat and bones of it." This is kind of the start of it. So walk the entire scene, create some sort of perimeter that's going to keep your evidence in, keep the spectators and the collectors out. The rule of thumb is to find the furthest piece of substantial debris and then make your perimeter another 50% larger than that. So let's say I find a big piece of wall 100 feet from my foundation. Well, then I need to expand my perimeter to 150 feet. And let's say I find another piece of debris out there at 150 feet. Well, now I've got to create my perimeter another 75 feet beyond that. And that's just so you can document all of the debris and potentially do some sort of explosion analysis where you could actually, and I don't see this done too frequently, but the potential is there to actually weigh how big of a piece, how much that piece of debris weighs, and then determine from there how much energy would be required to throw it that distance. But essentially, you're repeating that process and expanding your perimeter until you've basically encapsulated all your substantial debris. You're going to want to somehow establish, probably no different than a fire scene, one way in and one way out, so that you're not contaminating both your scene and other means of egress or people's yards or something like that. And then obviously, it goes without saying in this day and age, document the crap out of everything. So start no different than, say, examining an electrical system. Start at your source and work your way in. So start at your meter or regulator, or if for a propane system, start at the tank and the regulators. And then you're going to want to document all your piping, valves, and connections. One of the first things I do is I mark all of my connections and valves with a little witness mark. So that is the position that I found them in. You never want to disconnect any sort of piping because obviously that could be a source for a leak. So if you have to collect piping as evidence, cut the piping, place a witness mark at the cut so you could piece it back together, but you never disassemble piping because that obviously could lead to some spoliation issues. Document all your appliances, obviously make, model, serial numbers. Ideally, you're going to check the system for leaks before you start to do much of anything. Don't cause any more leaks than there were to begin with. So don't overpressurize it. And then if you do happen to find some obvious leaks, there are ways to basically isolate those and then test the remaining portions of the system. So some special equipment that we typically run across, I carry these solid paint markers. I use those for placing witness marks on piping. I'll show you some examples of that. We've got the leak detector. This is specific for gas. One thing you want to be aware of is if you do use this, you may want to wash it off with straight water just to mitigate any potential corrosion issues. Lower left, I've got two different types of gas meters. This Draeger is just, something like personal monitoring. So if you happen to be working and a leak occurs, you can detect that before it becomes an issue. Versus these combustible gas indicators, this is more of like your sniffer that you would be using to follow the piping and look for leaks in that manner. These fuel gas test adapters, company here in Minnesota developed these. Basically, if you take this little rubber banana, for lack of a better, but the test adapter, and you use a little clamp, you can use these to isolate your piping sections. So I could just use it as a fancy cap and seal it off that way. If, say, my piping broke during the explosion, I can also use it to connect different sized pipes. So if maybe my fitting broke, so I could go, down to a 1-inch pipe to a 2-inch pipe just because my adapter between those broke or is missing in the debris. From an analysis standpoint, one thing that has been done in the past is looking at or mapping the pressure changes based off of the evidence or the damage that you observed. So an example of this would be, I was listening to a presentation about the West Texas fertilizer plant explosion, and the investigators were going around and basically mapping the damage around or surrounding that fertilizer plant by, as an example, they said, all right, we found windows were broken, and I think they used like 1 PSI as that metric. So we know that windows were broken this far out. We had this, room doors dislodged at 1/3 of a PSI. So we had doors dislodged at this radius. We had, people thrown through the air at 3 PSI. So that was the limit here. And so you could actually map the pressure differences with distance from your origin in that respect. And just a way of kind of working your way back towards that epicenter or ignition source. Another thing you can do is actually map the displacement of walls. So this is kind of an example showing that maybe your origin is in the kitchen with all the walls of that kitchen heaving out from there. I don't see this kind of too often in the industry, but I think the bigger focus is identifying where the gas came from, and then identifying any number of potential ignition sources as opposed to the actual ignition source. I think where this probably may be most beneficial is more of like a bombing scene, or where you actually have an explosive and you're trying to identify where the epicenter or the device is or the explosive is, and find the pieces of that device so that you can piece it back together and develop that kind of evidence. So some other tools that can be useful are basically hand calculations and advanced computer modeling. So from a hand calculation standpoint, we can do some very general rough calculations, say just something as simple as, I've got a 20-pound propane cylinder in my structure. Is the contents of that cylinder even enough to get to an explosive mixture? So you can determine that based off of the volume, maybe the volume of available fuel versus the volume of the enclosure. Yes or no, that's not an acceptable fuel source. We can do stuff to the extent of trying to identify how long, given a certain sized leak rate, if we've done testing, leak rate or leak testing in the field, and we've determined that there's a certain size leak, we can actually punch that into a spreadsheet and determine how long it would take to get to an explosive mixture, given that leak rate and certain air exchange rates of a structure. And then to get on the real high end, you can use Fire Dynamics Simulator, FDS, which is good for modeling gas migration and filling. And then FLAX is basically another computational fluid dynamics program that is great at both gas migration and explosion damage. So and then I'll cut out here and we'll show a video quick. Hopefully everything works. So this is just a simulation of a gas explosion that Flax has done. And you can see it's a fairly advanced 3D model. Fulton, let me know if it doesn't work, but I'll keep rolling as long as it does. But you can see basically it's modeling a gas explosion in this industrial setting and showing the fireball as well as the pressure rise associated with that explosion. So that's kind of a Flax benefit, is that it will, it's a very advanced computer model, and the guys at GexCon are probably, oops. Gotta love the autoplay. All right. So we'll do a couple of case studies and then we'll wrap this up. So this first one was a single family dwelling in Madison. Bill and I actually worked this explosion a few years back with the Wisconsin State Fire Marshal's office. Essentially, right after all the kids came home from school, not too long after, this house on the corner blew up. And this was essentially the aftermath. So given the damage, I just kind of want you as the student to ask yourself, is this more low order or high order damage? And I'd probably lean towards high order myself, because there's not a whole lot left of this building. So as an example of what we did, we documented the gas meter. Here's the riser coming from underground. There's the valve that would then come into the regulator. The meter would have been right here. So we documented the piping all the way in. And if you're going to do any sort of kind of computer or calculation based analysis, you need to actually record and document the lengths and the diameters as well as all the fittings, because every 90-degree bend and fitting affects the flow rate of that gas. So we would have to document all of this. This is a 2-foot section going into a 90 with a 2-inch nipple, and then another 90, and then another 90, and all of that has to be documented. So in this case, they got all the debris off the structure. We were able to get into the basement and look at all the gas piping. Here are examples of how we documented. We cut all of this piping. So in this particular instance, we used tape. We numbered everything. So 9 went to 9. This is denoting that this goes to the water heater. Here's cut number 10. And we put a line here so you could match those cuts back up. Documented the furnace, all the piping coming into the furnace. Here's the dryer. And in this case, what we kind of noticed was here's the flexible gas connector to the dryer, and it was actually disconnected. The outlet for the valve on the dryer was right here next to this stud. So that was kind of an interesting data point that, of all the appliances in the structure, none of them had been disconnected at all. None, even after the explosion, none of them had broken or sheared off as a result of the explosion. So why is this one appliance disconnected? So we recognize that there might be some potential for some wrongdoing here, some suspicious activity. It was also kind of odd that if you look, this flexible gas connector is kind of twisted. So that's normally not a normal installation practice. So we recognize that this might be a potential data point. So we actually covered that connector end with a bag so we could actually submit that for tool marks to our lab and have them look for evidence of, was this disconnected intentionally? So here's another example just showing placing witness marks on everything to show how everything was put together so we could put it back together if need to later on. And this also allowed the private sector to get the same information that we gathered. And so here's the actual outlet for the valve on the dryer. This is the dryer flexible gas connector itself. So we protected those as best we could and then submitted those for tool marks analysis. Everything appeared to be tight as far as fittings were concerned on scene. There was some broken pipe, which is to be expected when a big house blows up and then falls down on top of it. The only appliance that was actually disconnected was the dryer, which was a bit of a, I guess, a red flag. So that piping was submitted to our forensic science lab in Washington for tool marks, and they came back and said, yeah, we've got tool marks consistent with disconnecting that dryer gas appliance connector, and it was something consistent with a wrench as opposed to like a pliers or anything like that. Bill, anything you want to add?
No, just what comes to mind when you say that was, well, how do you know that those tool marks weren't involved in the installation? And obviously we're leaving a lot of those details out, but we had found a tool in the area. I believe it was actually on top of the dryer. So in order to do that tool mark comparison to tool marks, you actually have to have a tool for the lab to compare it to. And after their analysis, they did find that the tool that was found on top of the dryer was consistent with those marks that were left there. But no, I think you got it.
Yeah, and it's they can classify a tool without having the tool for comparison. They just can't match the tool without having the tool. So they can compare. Pliers tends to have like a not a serrated edge, but it's got like a grip toothy surface as opposed to a wrench as a flat surface. And you can compare directionality with the tool marks. If the tool slips or anything like that, I'm going to have there might be some stripping or damage to the nut that is going to be opposite the direction of tightening it. So they can look at that directionality and determine, but again, like you said, there is kind of a cautionary. How do you know that they didn't maybe replace the dryer? And so at one point they had to disconnect it. So there would be an innocent explanation for those tool marks. And so that would have to be a consideration for sure. From a non-gas system standpoint, we did have a body in the basement. She was found wrapped in a blanket. They ultimately found a bullet in the pillow underneath her head. And then the medical examiner determined that she had been dead for weeks to months, if I remember correctly. And neighbors reported that they hadn't seen her for several weeks leading up to the explosion. So the ultimate conclusion was the husband ended up killing his wife, stashing her body in the basement for a certain period of time, and then trying to blow the house up on top of her to hide that crime. And his story kind of changed. It was, she wanted to commit suicide, but she couldn't do it herself. So she was hoping he would kill her for him, or kill her and save her the trouble. And yeah, kind of an interesting one. One of the weirder cases of my career for sure. Anything else, Bill, on that one?
No, I agree with that too. He actually was sentenced to life in prison. So obviously that's been adjudicated and we can talk about it. But yeah. Great case by Madison Fire, Madison Police. DCI was an incredible teamwork effort on that case. Definitely a career case for most of us. So
yeah. I don't want to claim any or all of the credit for that case. That was definitely a huge team effort by all involved. And looking back on this one, and we didn't have the capability at the time, but it might have been nice to try and leak test some things, just to kind of identify, everything looked finger tight or looked tight, but as far as fittings are concerned, but maybe doing some sort of leak test to verify that there wasn't any leaks. But otherwise, I think we had a really good case there. This is another case study. This is a single family here in the just outside of the cities of Minneapolis and St. Paul. Two occupants home at the time, both died as a result of the explosion or the subsequent fire. The husband had reportedly replaced the water heater just a day or two prior to the fire. And photo credit for these, Minnesota State Fire Marshal investigator Levi Roline was the one who took these photos. So this happened. This is the structure right here behind these trees on the corner. So this is a Ring doorbell camera, and this is where I'd always love to say I'd rather have video than and be lucky than good. But I've got a normal speed and then a high or a low speed or single frame. It's a relatively big boom. And then there was a subsequent fire that you'll eventually starts to break out. Kind of zoom forward here. This is actually like an Amazon delivery guy that was in the area. So here's kind of a slow-mo. But you can see, if you look quick, you can see, and I'll play it again, the flame front definitely begins in the basement and then extends outwards from there. So try and step through this. But if you look at that little basement window, there's the first glimpse of anything going on. And it kind of all heaves up from there. So kind of a neat video. From a documentation standpoint, this was the meter, the actual meter module that records the data had melted off here. But here's they're exposing the riser. The gas company collected the meter. These were my witness marks. So one of the first things I did when I got there, I kind of stood around for a couple hours because the fire department was still trying to, and the tech rescue folks were trying to get in and recover the victims. So there was a lot of kind of standing around waiting. So when I finally got in, the first thing I did was place these witness marks on every piece of piping I could get my hands on. So here's, the excavator comes right up to the foundation wall. Here's the gas meter. The gas line basically runs right across here and then across this I-beam. And then right about in here, there's a water heater and a furnace. And I believe there was a unit heater out in the garage, which is behind the camera. So here's the witness marks that I placed. This is coming down to the furnace, I believe, here. Yeah. Just another showing that here's that 90 from the gas line, 90 follows here. It actually had broken just above this I-beam, and that might have been because of the excavator. And he was a good excavator operator. He didn't do a whole lot of damage. But I think, just clipping that line was enough to break it. Not the best photo, but what you can see here is you've got a gas line coming in here, coming down the main line. You've got this yellow flexible gas appliance connector that comes to the water heater. And then here's another valve and a 1/2-inch copper line that goes off behind the water heater. Here's a little bit different view. So here's the gas appliance connector to the water heater. Here's the 1/2-inch copper line that goes behind the water heater. And if you look closely, the valve is open. So we found the end of that line. And if you look carefully, that's open and not connected to anything. And as is usually the case with many explosions, they come down to abandoned lines that are left uncapped. This family had formerly had a gas dryer, had switched to an electric dryer, and this copper line was actually used to be for the gas dryer, and nobody ever capped it. And so, if the homeowner's replacing this water heater and he's not careful, he either accidentally or intentionally, thinking this valve served the water heater itself, turned this back on, and that allowed that 1/2-inch copper line to free flow into the basement. And then a certain amount of time later, the place blew up. So a very unfortunate accident, but probably the majority of the explosions, at least residential explosions we deal with, are a function of these abandoned lines that are left uncapped and then accidentally opened up sometime down the road.
Cam, was the building occupied at the time?
Yes, both homeowners died.
Oh, they did. Okay, I saw that.
Yep.
Look at the Amazon, because we've had a couple here in Madison where the individuals have actually survived the explosions.
Yeah. Unfortunately in this one, I think the husband probably died right away, but the wife could actually be heard yelling for help for a while before she succumbed to either smoke or fire.
Gotcha.
So yeah, definitely a sad story in that sense.
Yeah.
So these photos actually came from my dad and when he was working at the fire department in St. Paul. And small explosion or small, not really even an explosion, but if you look here, not a whole lot of damage on the outside. This actually was more of less of an explosion and more of just improper operation of this water heater. So that obviously is not a good thing. Your water heater should not look like that. And a little bit of damage to the box with the two bottles of water. But ultimately, what they found was, as they were documenting the gas system, there's a crap ton of ice on top of this meter and regulator. And when they started to look at this a little bit more closely, you'll see that basically the entire vent is occluded with ice. And so, as we talked about before, that could lead to high pressure gas leaking into the system and causing bad, improper installation or operation of the appliance. And that's probably what happened in this case. So there's a couple of different ways they can get around that. They can put these little bells to help disperse that and keep ice and build up from that stuff. Excuse me. And you can have insects get in there and build nests or mice or rodents. Ice and snow can cause that blockage. So, different ways that they could get around addressing that issue in this instance. And I think maybe this might have been another way is to somehow provide some sort of cover or obstruction for that stuff to roll off instead of caking on the regulator itself. And then the last case study, if you look closely, a lot of low order damage, maybe not a lot, but all of these lower level windows are blown out on both these sides here that you can see. You've got the blinds and the window material blown out the window here. Here's two windows on the back side of the structure that were blown out. So definitely a low order, maybe 1 PSI, give or take, pressure increase from this. Here's that shield over the regulator on this set. But this is kind of the trick scene. So here you've got some low order damage to the window. From the inside. And here's some, one thing that's fairly common to see is some thermal damage from, the flash fire that occurs inside from the combustion of those fuel vapors. But here's kind of the analysis or the examination, and they're looking around and there's no real evidence of a natural gas leak, but they found these cans up on the shelf, and they found one can down on the floor. And lo and behold, you flip the can over, there's a hole in it. So, you've also got, if you look, there's a litter box in here. So maybe something caused that can or a can to fall off that upper shelf, fell down, punctured the can. And a lot of these aerosol cans have a flammable propellant in them that if that leaks, now you've got a potential fuel source. So this one can is what caused all that damage. is just the leaking propellant that got to a flammable mixture, came in contact with an ignition source, and boom. So to kind of wrap it up, most leaks are caused by something somebody did or didn't do, whether it's they opened a gas line or they didn't cap an abandoned line. Typically, we're more concerned with where the gas leak came from as opposed to what the ignition source was. We can usually identify any number of ignition sources, and while it's great to identify a single one, I think our biggest concern with a gas explosion is where did the gas come from? And so that's where our emphasis is usually placed. And the big thing here is, take it slow. One thing that kind of crossed my mind from the standpoint of differences in gases, for the most part, you're not going to see much of a difference between propane and natural gas. I've heard people say that, well, this caused way too much damage to be natural gas. It has to be propane. And frankly, there's not much of a difference when you're at that perfect mixture where you're toothpicking the structure. They're pretty much going to be the same. But, on the either upper or lower ends, maybe there might be a bit of a difference, but that's kind of it. So from reference standpoint, NFPA 54 and 58, there's this book, The Investigation and Control of Gas Explosions in Building and Heating Plants. 921 has a chapter on explosions. Kennedy on explosions is one of the few textbooks that focuses heavily on gas explosions, and kind of has ancillary chapters on explosives, whereas most explosion textbooks focus on the explosives part of it. And then CFI Trainer has a couple of modules too. So that's it.
Cam,
Thanks for everybody for sticking through it.
Thanks, buddy. I really appreciate it. So the test, Cam will give me some questions. We'll create a test. You can get a certificate. If you go over to our website, www.DCARI.org, there's a test tab there. Hopefully you have found this very informative, and we'll keep putting them out. So Cam, again, thank you so much.
Yeah, thank you.